Hello everyone, this is BEDRICH. I'm the CTO of Quantified Energy Labs, a Singapore startup focusing on drone EL imaging. This talk is about autonomous drone EL mapping for solar PV asset management. Let me start with making the case for high volume field EL. To date, EL is widely used in factories as part of their quality control. In comparison to IR and UV fluorescence, it does offer a higher information density, and it allows a direct comparison to the results from the factory. However, to date, it is not widely used. For example, for IR you only require a drone equipped with a thermal sensor, which is then sent meandering over your installation. In comparison to this, for EL, you do require a power supply to be connected to your strings, and the measurement is usually string by string. And this is where we come in. We try to offer a comprehensive turnkey solution consisting of hardware, that is, the drone with an autofocusing EL camera, switcher box and a power supply, as well as a software suite consisting of apps running on the drone, mobile and desktop devices. All our drone routines are fully automated, such as the routine you see in this video. Our deliverables are, besides an image database, a geo-referenced EL map and a quantitative score assigning every module a value corresponding to the assumed power loss. Let's have a look at some EL images. Here you see the result of a single row flyover. The camera field of view only contained 3 modules at the time. At this resolution you can see non-disconnecting cracks and scratches on the backsheet. You can also see, with lesser resolution without any problems, darker cells. The resolution will depend on the number of rows that we are flying over at the same time. Here we have a 4-row flyover, correspondingly the resolution is less. Here you see our lighthouse project, which we finished end of last year. Within 2 weeks of night measurements and a single drone, we measured over 120,000 modules, or 60 megawatt. We reached a scan speed of over 3 meters per second and we measured over 3,000 modules per hour. We consider this the world's largest EL inspection. Our working flow consists of 6 steps, but out of those I will only focus on the 3 steps corresponding to drone flight maneuvers on site. There's tour, which guides the drone to its target point, and then there's scan, in which the EL video is taken, which is then being processed to generate EL images, which are then mapped. In our first step, the planning, we generate measurement plans with a minimum user interaction. We usually generate 1 plan per combiner box or inverter, or usually up to 50 strings, so the number of strings that we think the drone should be measured within a single flight. As a data source, we use a CAD file or a PDF or previous mapping. There are 3 items of interest in our measurement plan. The first one is the start and landing point of the drone. Then there are obstacles, which could be houses, trees or fences or any other object that our drone could fly into while doing its measurement. And then there are PV strings, which we will further subdivide into PV arrays. PV arrays belong to a single string, but are regularly aligned. In this example, we have 1 PV string being divided into 2 PV arrays, 5 and 6. We will tackle those ones individually, as we will have the drone flying individually first to one array and then the other. In our measurement plan, we differentiate between target view and target point. The target view is the point we want our camera to look at the begin and end of every scan. Target point is the point we want our drone to be. The target point is shifted relative to the target view. The shift magnitude depends on the tilt angle of the module. For modules with little tilt, the shift is negligible. For modules with larger tilt, the tilt shift might be so large that the drone will be not above but at the side of the modules. Now that we got our target points, we would like to bring them into a logical sequence corresponding to the shortest flight time possible. A flight usually starts and ends at the home point and then goes to every single array once. If we would brute force through all different possibilities for our 6 arrays, we would have 23,000 possibilities. That is still a number that can easily be solved by a PC. However, if our measurement plan consists 50 single arrays, the number of possibilities would be so large that brute force is not an option. We therefore use a k-nearest neighbor approach to go from every single array to only the closest next arrays. If our drone path would be a direct line from one waypoint to the next, we might collide with obstacles in between. To avoid this, our drone path is generated from a 3D spline with an increasing number of knots. There would be no knots in this spline if there are no obstacles in between the 2 waypoints. To find those knot positions, we use a genetic minimization algorithm. We do not minimize towards the shortest drone path, but the shortest flight time, as the drone can fly much faster on a straight path than it would be on a curved path. This is an example solution consisting of a 3D spline path either around our obstacles or above them. Now that we spoke about the path, let's speak about the camera alignment during the tour maneuver. If the camera would be aligned fixed, so following the flight path, and if this flight path would not be straight but curved, for example going around an obstacle, for most of the time the camera would not see anything, because we measure at the night and our camera is not sensitive to much other things than the EL signal itself. To overcome this, we always align our camera with our target or the target view. This has the advantage that very early on we can verify that the right string is powered and we fly at the right point. If our target point is slightly misaligned, then during the tour maneuver we can easily shift and offset our tour destination. Now that we arrived at our target point, we want to prepare for the next flight maneuver, the scan. The scan consists of 2 steps, the alignment and the scan by itself. For the alignment, we try to align the camera's optical axis to be orthogonal with the PV surface. We also try to bring the array within the image center without any rotation. And we try to get a little space above and below the array subsection. This is to allow small positional misalignments during the scan. After we are aligned, we want to scan at the fastest possible speed. That means a speed at which we still have no unreasonable motion blur and a speed at which the frame average will have a signal-to-noise ratio above a certain threshold. Individual EL frames can have a very low signal-to-noise ratio, by the way. As we want to align the camera's optical axis with the PV surface, we might want to determine the PV module orientation. For this, we could detect lines, we could intersect those, and from the corner positions we could estimate a pose. However, especially for low signal-to-noise ratio images, those line detection results might not be reliable. In consequence, the pose vector might be jittered. If we would follow this vector, either the drone would be jittered by itself, or it would react very sluggishly if we tried to average those jittered values out over time. Fortunately, there is a shortcut. Usually we already know the PV module orientation, as most modules are aligned and oriented in the same way. If we do not know the orientation, we can just take a mobile device, align it with the edges of the solar module and just read the values for tilt and bearing. Additionally, we can further simplify. We can always define that the module bearing shall be equal to the drone jaw, means this angle shall be this angle. Additionally, we can define that the gimbal pitch or the camera pitch shall be equal to the module tilt. This is what we want because we want to have the angle between the surface and the camera to always be orthogonal. So we actually do not need to determine the orientation, we only need to have our delta x, y and z for camera alignment. And for this, we can just detect the smallest rotated rectangle, such as this one here. From the center of the smallest rotated rectangle to the image center, we can derive the delta x and y coordinate. And from the size ratio of our shorter rectangle side to the image height, we can derive our delta z. So what do we do if we can't see anything once we arrive at our destination point? There might be different reasons. One could be that the string is in an open circuit. However, our power supply would tell us that. It could be also that our drone, our camera are misaligned. Or a very common issue is that the wrong string is connected right now due to a mislabeling. Since we fly during the night, the safest way to find our EL signal would include no horizontal movement unless we have to. We therefore fly to a certain set height, then have the camera look downwards and slowly spin around the jaw axis while the camera slowly looks towards the horizon. In this spiral maneuver, we will stop as soon as we see the EL signal. We can then follow by either the scan or the tour maneuver depending on the distance to the target. This video will show you our current measurement routine, connecting the presented plan, tour and scan functions. First, string 1 is powered on through the app. Then the tour button is pressed and held. This aligns the drone with the target view. Once the right joystick is moved up, the drone will fly independently to the target point. When the target point is reached, the scan button is pressed and held. This aligns the drone with the PV array. When the record button is pressed, and let's wait for that, there it is, the drone will scan independently along the array. It will wait once the end of the string is reached or the record button is pressed again. Once string 1 is finished, a button will power off the current string and power on the next string in the measurement plan.
One is above us.
There it is. And now the next string is measured in the same fashion. During the routine, as you can see, the pilot does not have to do anything besides making sure that the measurement is done in a safe and quick manner.
Done.
The next steps I will keep brief. The result of the measurement is an EL video. This EL video will be translated into an EL image. For this, we need to detect those individual module corners. Every frame of a module corner will be aligned on top of each other. Here you see 15 EL image frames aligned for one module. Taking a frame average instead of a single frame has multiple advantages. One being that you can reduce the noise by the square root of frames being averaged. You can also improve the resolution if the frames are aligned precisely. I had a post on the 2019 annual reliability workshop on that. You can also remove transient features. Transient features can be those dead pixels that you see here, or even birds flying over your module. After averaging, the remaining perspective error is corrected and the modules are placed into the right spot within the PV array. Further, cells are being detected and the modules are being rated. After a manual approval of every EL array image, the EL images are pre-aligned in a map. The pre-alignment of our EL modules is possible because we record the drone position and the camera orientation during the recording of the image. Although we use RTK GPS, there are still small position errors possible. Therefore, we manually align images to their base map. A snapping algorithm ensures that the alignment is precise and quickly. After the alignment, the resulting map is uploaded to a cloud and PDF reports are generated. Here's our roadmap for 2022. We will start this EL service in the US, basically right after this conference. The 3 drone maneuvers that I presented, tour, scan and find, are all autonomous routines by themselves. Additionally, all target points and the switcher box channels are usually known in prior. At the moment, the measurement plan is executed semi-automated. That means that the pilot will still manually start and land the drone, he will manually change the measurement plan step, and he will execute one of those 3 routines. In 22, we plan to further automate this execution. Whether it will be a single-click automation, we are not quite sure because we want to keep the pilot engaged during the measurement to ensure that everything is safe. Additionally, we plan to develop an empirical power loss model based on our big data of EL and IV measurements. This is all from my talk. I thank you for your attention, and if you have any questions, please ask.